This morning I'm going to present some of my works on building these lexical resources for facilitating natural language understanding. I will start by talking about the work I did for my thesis on building a lexical resource on verbs, and then I will talk about some of my current work on building bilingual translations for many languages. And first of all, why verbs? Well, one of the most compelling reasons I find for building the resource on verbs is that for many languages, the verb is the organizational core of the sentence. So in this sentence, the verb bought organizes all the other words in the sentence into their roles and also expresses the relationship between these roles. And for that reason, understanding the meaning of the verb is one of the keys, I thought, for understanding the meaning of the sentence. And another motivation is that I believe that for the vast majority of relations, we can express it by using verbs. And for example, for this group of semantically similar verbs, which take a subject of type person and object of type person, we call it the type signature of the verb. We can map it to the spousal relation in the world. And using this assumption, then we believe that a high coverage verb resource can therefore provide us potentially with high coverage of relations to express the meaning of any arbitrary text. And so I also believe on linking these verb predicates to knowledge bases, because, for example, by linking these type verbs, we call it type because it has a type of the subject and object entity. By linking it to the knowledge base such as NELL, which we develop in CMU, we can tap into more information about the relations that the verbs express and the entities that the subject and the object-noun phrases refer to. And having access to this extra information that is not otherwise expressed in text can help us do inferences that can help us disambiguate the meaning of the sentence, for example. So the verb resource that we built is called VerbKB, and we construct it by leveraging on three things. One is the high coverage text corpora. Another one is a knowledge base with a rich type system over the entities. And we also utilize other pre-existing linguistic resources, such as WordNet and Thesaurus. And the VerbKB contains about 65,000 unique verbs and preposition. And we map it to about 200K relations. And each are typed with NELL categories and can be organized into a taxonomy based on NELL hierarchy of categories. And to the best of our knowledge, this is the largest verb resource in terms of the number of unique verbs that it contains. And so what do the VerbKB contains? There are two semantic knowledge about verbs that we have in the VerbKB. One is the mapping of verbs to the knowledge-based relations, and the other one is the mapping of verbs to the changes in knowledge-based relations. So, for example, both marry and divorce with subject type person and object type person express the spouse relation, but marry initiates it while divorce terminates it. So the representation view that we have is on one side we have the verbs, and on the other side we have the relations, and we believe that some of these verbs express the relations, while some others express events that in turn initiates or terminates these relations. So the overarching goal of building this verb resource is to provide a bridge between the surface form verbs and the relations in the real world that are contained in the knowledge base. So to give you an idea of how the VerbKB looks like, I'm going to show you some of the things that it contains. So these are the mapping that we have in VerbKB between the verbs and the relations in NELL that the verbs express. So for example, like for the verb, for the relation book, writer, which takes book as argument 1 and writer as argument 2. Some of the verbs, the type verbs that express it is book is written by writer, or writer write books, and so on. And another thing that we have is the mapping between the verbs and the initiation or termination of Wikipedia relations. So in this case, for the spouse relation in Wikipedia, some of the things that initiates this relation is the addition of the verb person marry on date, and the deletion, if you see there's a negative sign, means deletion of the person gives something to the other person, I guess the spouse. So when these things like person is engaged to the other person being removed from the Wikipedia page, and the word marry is being added, that shows that the spousal relation is beginning. And for ending the relation, we see things like an addition of the word person filed for divorce in some date. That shows that the info box will be changed for the spousal relationship. That means the end date will be added to the info box. And all these are contained in our VerbKB, which we put them all together. And this shows like we can search for verb, and then it shows for all the verb, all the type signatures that are possible for this verb. So you'll see some strange things. And the frequency of occurrence in the data, and the relations that it expresses in the knowledge base. So for example, this links to the wife of relation in NELL. And you'll see all the, also if it initiates or terminates some relations in Wikipedia info box. And you can see the more data, which are the mentions of the type verbs in the clue web corpora and the frequency of them. So you see why person marry animal is one of the type signature of the marry, because in our corpora there's a lot of things about girls marry frogs, I guess. That's one of the things. But there are news articles about some boy being not really literally married, but to a dog or something, yeah. So these are from clue web corpora, and we extract the subject verb object triples from them. And so these are the idea of VerbKB, and so I guess to give you an idea of what it contains. And now I'm going to talk about the methods that we use to actually construct this. The first one that I'm going to talk about is how we map the verbs to the knowledge-based relations. So the idea that we have is, on one side, we have the knowledge base with the relations, and we also have the entity pairs that instantiate these relations. And on the other side, we have the verbs. So the idea is that we use the web text to bridge the knowledge-based relations to the verbs. And to do that, we find mentions of the entity pairs in the knowledge base in the web text, and then using the statistics of which we then map the relations to the verbs. And
I have a question. Where do the relations come from?
They are from NELL knowledge base.
And isn't NELL mining the relations from the text itself? So I'm trying to see what is the right circular look here.
Yeah, I guess what we are trying to do is exactly that, because NELL has already some entity pairs that are labeled. So we use that as initial way to map the relations to the verbs. But we also are going to use the unlabeled entity pairs that NELL still hasn't extracted as additional signals for learning the mapping from the relations to the verbs. Yeah. So for the web text, we extract 150 million subject-verb-object triples from the clue web corpora. And so another thing that we observe is that the argument types of the verbs can help disambiguate the relation. So for example, the verb play, it can express a multitude of relations. But if we know the subject and the object of the type of the subject and object of this verb, then it can help us disambiguate the relation that it expresses. So instead of mapping verbs to relation, we are going to map the type verbs, which are the verb whose subject and object are typed with NELL categories, to the relations that it expresses in NELL. And because we have both the labeled entity pairs in the knowledge base and the unlabeled subject, verb, object triples, we can learn from this unlabeled data in a semi-supervised manner. So we use expectation maximization. And the way we do that is we try to build a classifier that, given an unlabeled entity pairs, we predict the relation labeled for this entity pair using the verb that exists between them as features. And so the parameters are the probability of the relation and the probability of the verb given the relation. And this gives us the mapping that we want from the relation to the verbs. And in the E step, we use the current classifier to label the unlabeled. In the expectation step, we use the current classifier to label unlabeled entity pairs. And we use type checking as an additional constraint, so that the unlabeled entity pair, such as Bill Clinton born in Hope, that is unlabeled entity pairs, we map it to the relation whose domain and range match the subject and the object types of this entity pair. So the relations has an argument 1 and argument 2. For example, book writer, the argument 1 is the book and argument 2 is the writer. That's the type in NELL. And so we constrain it such that an unlabeled pair, we know the subject and object type. So we only label the entity pairs with the relation whose argument 1 type match the type of the subject and the argument 2 type match the type of the object. Yeah, that's the domain and range of the relation. And so we also use another constraint to make sure that we label the unlabeled entity pairs consistently. Two of the constraints that we use is the subset constraints. For example, if we already label an unlabeled entity pair with the relation CEO of, which is a subset of works for, then we also label this entity pair with works for relation. And on the other hand, if there are two relations that are mutually exclusive, once we label the unlabeled entity pair with a CEO of relation, for example, we should not label it with the competes with relation. So we incorporate this constraint using the mixed integer formulation following the work of Bhavna here. And given for here the bit assignment for the entity pair EM and EN, bit vector assignment, this constraint is saying that if relation I is a subset of relation K, then if I already labeled this relation with relation I, then it should also be labeled with the relation K, otherwise impose a penalty. And if they are mutually exclusive, then if I already label one with a relation I, then I should not label the other one with the same one with relation K, otherwise incur a penalty. And so the MIP formulation try to maximize this probability of label assignments after penalizing for the constraint violation. And these are in the E step, in the expectation step. And then in the M step, we use both the labeled entity pairs and the unlabeled entity pairs to re-estimate the parameters of our classifier. And these are the parameters, the probability of the verb given the relation that gives us the mapping from the verbs to the relations. And we experiment this by mapping, learning a mapping between the English verbs to the English NELL relations, as well as the Portuguese verbs to Portuguese NELL relations. And we compare the mapping to a current pattern extractor that NELL uses to extract relation, using patterns that occurs between the entity pairs. And we also compare it to DIRT that measures the similarities between verbs and a relation based on the overlap of the entity pairs that they have. And we evaluate it for the task of relation extraction. So we can see here that learning from unlabeled data, so the purple bar, shows that learning from unlabeled data improves the recall quite a lot, and overall the F1 score too. And this happens on both the English NELL and the Portuguese NELL. And as you see here, the Portuguese NELL has lower recall because it has lesser labeled entity pairs, because the English NELL was developed much earlier than the Portuguese NELL. So it has less labeled instances. So in order to add more instances to the Portuguese knowledge base, since they share a taxonomy, we can technically add labeled entity pairs from the English knowledge base to the Portuguese knowledge base. So for example, add this additional labeled entity pairs. But then the challenge becomes finding the mentions of these English entities on the Portuguese web text. So the way we do that is we use interlingual links in Wikipedia to help us map the English NELL entity to its Portuguese noun phrases. But one entity can be mapped to several possible Wikipedia pages. For example, Brad Pitt could be Brad Pitt the actor or the boxer. So the way we disambiguate it, we use the NELL knowledge to disambiguate. And the idea is that relatedness in NELL knowledge base implies relatedness in the Wikipedia page. So for example, here, given this particular Brad Pitt in NELL that has links to Angelina Jolie and so on and so forth, we can use the personalized page rank to find that it is actually the Brad Pitt the actor, because it also has links to the same entities that connect back to the entities in NELL knowledge base. So using this, we map the English entity to Portuguese noun phrases. These are some examples of the map entities. And the interesting thing is, by mapping to another language or another knowledge base, we can actually get more information. For example, the full name of this guy, Utamaro, is Kitagawa Utamaro, by mapping him to the Wikipedia pages from NELL entities. And so adding this, we sort of double the number of labeled entity pairs in the Portuguese knowledge base. And you can see the improvement in recall and the overall improvement in compared to the purple bar, overall improvement in the F1. So it shows the benefits of adding more information from different knowledge bases. So these are some examples of the mapping that we have from verbs to relations in both the English knowledge base and the Portuguese knowledge base. And also, since we build a classifier that classify unlabeled entity pairs, we also get new instances that are not in NELL, that are not yet in NELL for these relations. And so that's the first part, how we map the verbs to the knowledge-based relations. The second part is, how do we map verbs to the changes in the knowledge-based relations? So the way we see it, when state-changing events happen to entities, for example, this lion, it changes the lion itself and also the relationship of the lion in the real world. And it's reflected, for example, in the Wikipedia, in the info box information. So discovering what changes in the real world can help us update the knowledge base. So how do we learn this mapping between the verbs and the knowledge base relations that it initiates or terminates? So our approach is, we want to learn this correspondence by using a temporally stamped corpora. The idea is because from our previous study, we see that when an event happens to an entity, the words surrounding the entities actually change. And when we zoom into what changes, we see that some of the words that change before and after the event show the events that happen, as well as the state change, the actual state change that happened. And by detecting this change, we can update the information in the knowledge base quite effectively. So using this idea, then we want to find a corpora that have both the temporal stamp and the text change and the accompanying knowledge base change. One of the corpora that we find to have both is the Wikipedia revision, because it has both the text and the info box information that reflect the underlying knowledge base relations about the entity. So for example, in this particular date of the revision, when this person was married, additional verb was added to its page, and info box was also changed. So we can find the correspondence between the adding or deleting of verbs from the text page and learning the corresponding relation change in the info box. And the way we do that is we use maximum entropy, and we learn a classifier that takes an unlabeled Wikipedia document and predicts the state change label using the verbs that is being added or removed from the page as features. And the weight that we learn here, we can use it as to weight the confidence of the mapping between the verbs and the changes in relations. And however, as usual, Wikipedia is very noisy. When a page is updated, like somebody died, for example, or somebody get married, a lot of other things in the info box can get updated. So to deal with this noise, we also added these constraints such that we can get a better, more consistent verb feature to state change mapping. We do same constraints like mutual exclusivity and subset constraint, and we use the MIP formulation to incorporate them. And we see that when we add this MIP formulation, it actually improves precision, reduce recall a little bit, but overall it improves the F1 of the classification. And these are some examples that I've shown before in the VerbKB about the verbs to the relation changes mapping, the initiation or begin, and the termination or end of the relation. And on VerbKB, the last one is I will talk about the third part, which is to use verbs to extend the ontology of relations in the knowledge base. Since NELL relations are manually created, curated, it has only a couple of hundreds relations. But for a lot of verbs that we have in our subject-verb-object triples, they are not mapped to any of NELL relation. So for example, the verb support with a subject of product, a subject type product and object type programming language. It occurs like almost 1 million times in the SVO triples, but it has no corresponding relation in NELL. So, and yeah.
So one thing, abstracting these type signatures and counting over them, are you just counting over all possible type signatures?
Yes.
Okay.
Yeah, it's out of context. Yeah. We'll see that it will create problems later. Yeah. And so at the beginning of the talk, I talk about how we need to support natural language understanding, we need to have a knowledge base with a vast vocabulary of relations to express meaning of any arbitrary text. So more relations can also be beneficial. It can create denser knowledge-based graph and better inferences. I think Matt did a lot of that work. Yeah. And so the idea that we want to have is we want to cluster these semantically similar type verbs and propose them as new relation in the knowledge base. So the way we did that is we realized that distributional similarities alone are not enough. There are some recent works that show that using the semantic roles of the verbs or the type signatures of the verbs can help in clustering these verbs into better senses. And we also incorporate the synonymy and antonymy relationship from existing linguistic resources to encourage similar synonym verbs to be in the same cluster and antonym verbs to be in different clusters. And so the method that we use is first we deduce the type signature. We find the type signatures of the verbs. And for example, follow can have either the sense of an event following, an event outcome following an event, or follow in the sense of moving along some direction. And then we find similarities between these type verbs. And then we cluster them such that the cluster will be semantically similar and similarly typed verbs. So the way we generate type signatures for verbs is for all the subject, verb, object triples that we have in our Clue Web corpora, we assign type to its subject and assign type to its object based on NELL noun phrase to category mapping. This is static mapping. So we did it like out of context, just based on subject and the object noun phrases. And then we also generate all the possible type signatures for a particular verb. And then we also count the frequency, and we compute the selectional preference of the verb, which is the how high is the association between a verb and a particular type signature. And we rank them, and we threshold them. And these are some of the type signatures that we learn for the different verbs. So for example, play, it can take person and person play game as one of the type with 6.3% of occurrences in the corpora. And you can see that there are some wrong, well, interesting or weird ones, like location can die on a particular date, or location can die of physiological condition with a much lower frequency, but this happens because we do the typing of the subject and object out of context. So Davis, for example, can be both a person or a location. So this is how we end up with some of these wrong so-called type signatures for verbs. And then once we find the type verbs, the type signature of verbs, we compute the pairwise similarities. We compute both the global similarities, which we define as the similarities between untyped verbs, and the local similarities, which is the similarities between the verbs that have similar type. And for measuring similarities, we use a DIRT idea that measures the similarities between two verbs based on the mutual information that is computed based on the number of entity pairs that these two verbs have in common, like this number of subject and object pairs that the two verbs have in common. And then recently, we also experimented with measuring similarities based on the embeddings of these type verbs. So we try and learn the embeddings of the type verbs, taking into account both the distributional similarity as well as the type of the verbs. So the idea that we have is given triples such as this, the noun phrase subject and the noun phrase object and the type verb, we learn the embedding of the type verb by framing this type verb as translations that operate over the lower dimensional embedding of the subject noun and the object noun. So following the work of Bordes in 2013, we want to the embedding of the object noun phrases to be close to the embedding of the subject noun phrase plus the type verbs if these triples are observed in the Clue Web corpora and far away otherwise. And so these are the recent work that we did, and it gives quite interesting prediction, prediction performance for tasks such as sarcasm detection and then control, like whether somebody is in control based on what kind of verbs they use and what kind of subject and object they use. But this is a current work, so I will not talk too much about this, but you are free to ask me later. Yeah. And so once we got these pairwise similarities, For example, for the global similarities, you can see that for the verb follow, these are the nearest neighbors, and you can see that they are synonyms of the verb, but they express different senses of the verb. But if you go into the type verbs, you see that the different type verbs, nearest neighbors, actually expresses some sort of the sense of the verbs. So for example, the sense of the verb follow as in moving along something, or the sense of the verb follow as in happening after something. And so we want to use both of this information, the local similarities and the global similarities, to produce the clusters. And we also add the constraint of synonymy and antonymy. Quite simply, we remove edges between antonym verbs, so they cannot be in the same cluster. And we add edges if they do not already exist between synonym verbs. And we use the global similarities as a kind of proxy, because not all the synonyms are available in the existing linguistic resources. So to have higher coverage, we also use these respective global neighbors and local neighbors as proxy for synonymy. And to do the cluster, we first compute the... Yeah.
And how about antonymy?
Oh yeah, we do something simple in this case. We remove edges between antonym verbs. But yeah, we can think about like using the counterfeiting and retrofitting of the word embedding that tries to push the synonym embedding closer in space and antonym further away in space. So those are some of the possible things that we can do. But I didn't do it here. Yeah. And to cluster, we first arrange these types into hierarchy. Why? Because we believe that the clusters of the children of a particular type can inform the clustering of that type. We'll see it happens, like for example, if we cluster at the person-person level, the word stamp for, which means making a speech in support of someone, is clustered with the wrong kind of words. But if we go to the children level, we can actually get a better word nearest neighbor to these type verbs. So the way we do the clustering is we first cluster from the bottom of the hierarchy, and we then propagate these clusters up. So when they are propagated up, they become a point that cannot be broken into separate clusters at the upper level. And so the result, we can see here that for some very highly ambiguous verb, such as have, like city have attraction, person have physiological condition, adding the type and clustering based on this type, and as well as the distributional similarity, can help us actually produce the right sense of the verbs. Like this is possession, this is experiencing something or feeling something, as well as play. Somebody can play a musical instrument, or acting as someone, or playing a hobby or something. So those are the things we learned, that by adding types, we can actually get a better representation of verbs. And so in the experiments, we evaluate the quality of these verb clusters by comparing them to the reference clusters. In this case, we use WordNet-based reference clusters. And we compare it to PATI, which is another high coverage resource on patterns for relation extraction, and PBDB, which is a paraphrase database that has for each phrase the different paraphrases of the same phrase. And we compare using we compute the V measure, which is measuring the completeness and homogeneity of the resulting clusters compared to the reference clusters, as well as the paired F measure and the node-based F measure. The paired F measure measure the precision and recall as in classification. So two verbs that should be in the same clusters are positive instances, and two verbs that are not in the same clusters are negative instances. So we can measure the paired F measure for those our clusters compared to the reference clusters, as well as the node-based F measure, which is simply for each of our resulting cluster, find the most similar cluster in the reference, and then measure the purity and the inverse purity as precision and recall, respectively. And the previous work has shown that if you can balance between this F measure and F score, then it tends to produce the best clusters by human judgment. And so we can see here, PATI has very high V measure, but low F measure because PATI clusters are smaller. And while PPDB clusters have have slightly lower the V measure, but higher F measures because they are larger clusters. And V measure tends to favor smaller clusters. And this we see in the actual clusters. So if we look at the best and the worst clusters that align to the WordNet cluster, we see that PATI gives clusters that are small and just, it just have variation of the same verb but with different preposition, while PPDB has more verbs per clusters, and VerbKB is actually in between these two resources. And we see that PATI for the worst aligned clusters to the reference clusters, PATI clusters are small, so it cannot capture big clusters in WordNet. And PPDB, on the other hand, is too large and contains all the different senses of the verb, while VerbKB has, even though it doesn't match exactly, it has the right sense of the verb.
How do you define the reference clusters based on the WordNet hierarchy?
So WordNet has synonym sets of the verbs.
So the synonyms are the clusters?
Yeah. And like if, I think that answers the question. And so here, these are the difference between all the different resources on verbs. As we can see that we have used both the type and the constraints to compute similarities. And we deal with polysemy by using the types of the verbs. And then to derive the verbs, the types, we actually use some sort of measure of selectional preference of the verbs. And we also have links to both the relation that it expresses as well as the change in relations. And so in future, we want to align this knowledge about verbs because we have many. We have VerbNet, we have WordNet, we have FrameNet that has verbs, and we have PATI. And we want to be able to put all of them under one roof, hopefully. Like, that will be nice. And we also want to extend it to multilingual resources. And this brings me to my current work in University of Pennsylvania with Chris to try and learn bilingual translations for different languages, especially for low-resource languages where we don't have many parallel text. So the goal that we want to do is we want to reduce the reliance of machine translation systems on parallel text by using more easily available monolingual data or bilingual data such as Wikipedia. And the idea is we want to be able to measure translation equivalence computed on separate monolingual corpora. The original idea was by one of the things we can measure is contextual similarities, that words appearing in similar contexts even in different languages are probably related. So in the previous work, the way they did it is for each word or each foreign word, we collect the context. And then using some seed bilingual dictionary, we project this context to the English space. And then once we get the projected vector using the bilingual seed dictionary, we can then measure the similarities to other words in English. And with this, we can find the similarity between a foreign word and an English word. But there are many other ways to do it. We can do a temporal similarity. For example, words tend to surge or decline at different time period, like in news, for example. And we can find topic similarities, like words that are similar appear in similar Wikipedia pages. We can find orthographic similarities because words are written similarly, almost in related languages. And we can also find bilingual dictionary of related languages. For example, for like my native language, Indonesian, we have a lot of loan words from Dutch. And Dutch is a higher resource language that has already translations to English. So we can use the Dutch to English translation to help bridge Indonesian to English translation. And then we have also a lot of monolingual word embeddings that we can train better by day. And then we have images, like different words in different languages. They can share similar images. That such signal can be used to measure translation equivalence. And so how to combine all of them? So previous work have used supervised method to combine it. And in this work, we want to propose a new framework, actually, by to combine all this information using matrix factorization, which has been shown to be quite effective for in the area of relation extraction to combine noisy distance signals. And so these frameworks, where we treat the words in English as rows and the words in foreign language as columns, we can populate it with observed translations. And then we can use it to infer the missing translation by using a matrix completion approach. For example, for low resource languages such as Indonesian, we can use related languages such as Dutch with some of the translation to English to project the translation from Indonesian to English. And we use the Bayesian personalized ranking. Yeah. Do you have a question? We use the Bayesian personalized ranking because we only observe positive instances, which is the positive translations. So Bayesian personalized ranking has been shown to be effective to learn in the presence of positive-only data. And so it's also extendable. You can add many different signals. And the idea of this BPR is to maximize the difference between the values we assign to the observed cells minus the value that we assign to the unobserved cells. So the cool thing about it is that each of these values can be approximated using different methods. So for matrix factorization, the values can be approximated by learning two lower rank matrices and compute the dot product of the two vectors from the two low rank matrices. And however, BPR and matrix factorization in general suffer from cold start issues where we have not enough observation for a particular entry in our matrix. For example, this word has no associated observations, so it's the matrix completion approach will not work as well. And so to do that, we want to alleviate it by adding auxiliary information in the form of word embedding. And so for each of these words in English and each of these words in Indonesian, we can learn their word embedding separately on the English corpora and in the Indonesian corpora. And then we can add them as auxiliary information. So the idea is that the scores here will be approximated by this dot product of two vectors, where the vectors theta e is, in a sense, it's a log linear classifier that for each of the row, it gives a score given the feature vector of the foreign word, or the word embedding of the foreign word, theta f. So using this, and beta is just the bias term, and using this we can add the, even if they don't have an observation in the observed translations part, we can use the word embedding to help us find which word in English it translates to. And we can get better embedding by learning actually the projected mapping from Indonesian to English, for example. And the idea of these works, or a lot of works actually in this space, is we can learn a mapping, for example, W, to map this monolingually trained word vector in Indonesian to the English spaces. So we can do a linear mapping or a nonlinear mapping to learn W using neural network mapping, for example. And given this, once we learn this W, given an unknown word with the word embedding, we can project it to the English space using the mapping and get the similarities in this projected space. And we find that this gives a better translation than if we only use separate monolingual trained word embeddings. And so instead of using the monolingual word embeddings thesis, we learn the projected word embeddings and use it as our auxiliary signals for measuring translations. And so in the experiments, we use for observed translations, we use Wikipedia interlingual links, as well as the translation of related language, for example, Dutch to English, based on these mechanical Turk dictionaries that Chris' student, Ellie Public, already compiled for 100 languages. He has the mechanical Turk translation to English for 10,000 words for each of the 100 languages. And these 10,000 words come from the 10,000 words most frequent words in the 1,000 most visited Wikipedia pages for that language. And so we can think about it like this Wikipedia and Wikipedia plus the translations as the observation in our matrix, and we can use it to infer the missing translations in the matrix using matrix factorization. And we can also use the projected word embedding. We tried two things. We tried a linear mapping and also a simple 4-layer neural network mapping, and use this formulation to measure the score of the missing translations. And we also combine the two using the idea from collaborative filtering to to back off. So once you see a word that doesn't have enough associated observation in the matrix, you back off to using the auxiliary information. So these are some of the results that we have for Indonesian to English. As you can see that for some words, Wikipedia or interlingual information already gives the right translation, but you see the other translation at the top 10 is quite diverse and not really related to that word, but using the projected word embedding, we can find also related words to that. And this is interesting because for some words, it only finds related words, not the right translation. But using like mechanical Turk additional information, we can get the right translation. And overall, if we combine it, we can have both the right translation and the right related words. And for this, we don't have, because this is cold start issue that I mentioned before. It doesn't have enough associated observation just using Wikipedia. And so this shows that cold start issues can be alleviated by using the auxiliary information from the word embeddings. And this is the accuracy that we got on benchmark data sets, which consists of three data for high resource languages, Italian to English, Spanish to English, and Dutch to English. And we see that combining information actually help improve it. The baseline is just using the linear mapping to learn the similarities between the foreign words and the English words. And so this, we also run it on 26 languages from high resource to lower resource. And we see that combining information always helps. And we also see that the performance depends very much on how many monolingual corpora that we have for training the word embedding. So for Somalian, the Wikipedia only have about 945K tokens to train the word embedding. So it doesn't give really good results. But the more we have, the better the performance will be. And also it depends on the size and the quality of the mechanical Turk dictionaries that we use to train the mapping between the projected spaces. And the other thing we did is that besides using this text-based, we can also use the visual similarities. And this is previous works have tried to do this. It's very interesting because you can think about image as a language-independent signals. You know, in different languages, candle are similar. And this is especially true for concrete nouns. And one of the Chris group has created this interesting visual data set that we will release soon. And it has for 100 languages, up to 10,000 words on each language, up to 100 images for each of these words. So it contains many, many images. And then also for each of these words, it has the images of the English translation, up to 100 images for each English translations. And beside that, we have also the feature factors that we generate for these images, the CNN, SIFT, and histogram feature factors for each image beside the image itself. So you can see here using the CNN features, these are the top 4 nearest neighbor for the image for kucing, which is the word for cat in Indonesian. However, this has a downside, of course, for like abstract nouns, such as concept. It cannot find the right translation in the top neighbor, nearest neighbor, because the image for the correct translation is very different from the image in the Indonesian word. So we believe that adding other signals of translation can help in this data set. So we also experiment on this data set, and we try only text-based, and we tried only visual-based, and we also combine the two. And we remove a lot of the mechanical Turk dictionaries that we use as seeds because it's in the test set, so we don't use it to learn the mapping. So for this, you see with very little seeds, it only finds the related words for plate in Indonesian, but the visual one gives the right ones because visually they are very similar. And adding them actually, actually improve the performance further. And this is true like for verb words, because for verbs, the images are very diverse. For example, menyelidiki is explore, and the two images, Indonesian and English, are very diverse. But adding the text-based can help alleviate the rank of the right translation. And also for ambiguous kind of noun, I think, like pelayaran, both the Indonesian and the English images don't show the right translation in the top 10, but adding them together, actually, you can get the right translation. So we show here quantitatively that the adding both the text and visual can improve the accuracy of the translations on this data set. And so here, in this work, in the current work that I'm doing in the bilingual translation induction, we show that BPR can be an effective framework for incorporating all these distance signals, multimodal signals for measuring translations, and we can also add more signals for measuring the translation. And in conclusion, I presented two things. One is the verb from resources, and the other is a little bit slightly different, but maybe will be related. Lexicon translations for many languages. Okay. Thank you.